Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from automatic generation control. And the name of a topic is steady state analysis of single area load frequency control. Already we have gone through a complete block diagram representation of single area load frequency control. We know what is delta PC. Delta PC is nothing but what? It is change in the speed changer setting. KSG upon 1 plus S into TSG. This is nothing but speed governor transfer function, or you can say speed governor block. Then delta YE, already we have gone through why this Y is there, why this E is there. You refer my previous video sessions. Then this will be your turbine, we can say turbine block diagram. Then this will be a power system or generator load model block diagram. This is your regulator. This delta PD is nothing but change in the load demand. Now from the overall block diagram of a single area load frequency control, it shows that there are two important incremental inputs to the load frequency control. What are the two inputs? First one is delta PC of S and second one is nothing but delta PD of S. Now it is not possible to prepare a transfer function with two inputs. We should have one input and one output system. So now we will take one case. What we will do, I'll write it here. Let me take here case A, and in a case A I will treat this delta PC will be equal to 0 and delta PD is available, or it is acting. Now let us consider that whenever this speed changer has fixed setting, that is when we say this delta PC equal to 0 and only a load demand is changed, then this particular condition is called as a free governor operation. This is called as what? Free governor operation. Now if you see, this is your unstable operation. Why it is called as unstable operation? Because here there is no any control over change in the load demand. Even though your load demand is increasing or decreasing, there is no any change in the speed changer setting. Or we can say there is no any governor control. That's why it is called as free governor operation. Or we can say unstable, because load is changing or load is increasing or decreasing. There is no any control over a speed changer setting. So for such operation, the steady change in the frequency for a certain change in the load demand by an amount delta PD can be written as. Now delta PD is change in the load demand. So we can write in Laplace transform, we can write it as delta PD of S upon S. Now why we have taken here S? Because what this delta PD indicates? This delta PD is nothing but change in the load demand. Now the change in the demand is not like a gradual, it might be a sudden increase or sudden decrease in the load. So this sudden change, I write it here, this sudden change always it is represented by a step input. It is always represented by what? This is your step input, because it is a sudden change. And the Laplace transform of a step input, it is nothing but what? It is nothing but 1 by S. So in place of delta PD of S, what we have to write? Delta PD of S upon S. And if you see unstable, or I can write it here another word also, it is also called as uncontrolled operation. Why? Because even though your change in the load demand, but there is no any change in the we can say governor setting, that is delta PC. So now let me reform this block diagram. So I will draw it. What I am going to do now? I am going to consider this particular this delta PC will be equal to 0 and this particular will acting alone. So I will just copy paste this diagram because I have already drawn this. So let me draw this diagram here. Let me take this diagram here. So we will get such kind of diagram for a case A. This is delta PC equal to 0. Now this will be your input, this will be your output. Or what I just did, I have just redrawn this diagram. This delta PD, then KPS, delta F output, and everything which is to be there here, it will be act in a feedback. So it looks like this. Delta PD of S, then this. Now based on this, what I want to write? I want to write a transfer function. Now basically you have seen how to write the equation of transfer function. This is your g of s. This total is nothing but h of s. So how you can write g of s upon 1 plus or minus g of s into h of s. This is the formula of a transfer function. Now please remember, here input is negative. What is this? Input is negative, so it will be what? Minus g of s upon 1 plus g of s into h of s. Okay, so why this plus is there? Because here when input is negative, so it will be opposite here, 1 plus g of s into h of s. So I will write it here directly as, therefore output is what? Delta f of s. So I will write it as delta f of s. Okay, then here what is our condition? Delta pc of s will be equal to 0. So how I will write g of s? So kps upon 1 plus s into tps. So this is my numerator, I can say, divided by, let me write it here, 1. Okay, 1 plus g of s into h of s. So I'll directly write it like this. If you see this kt, kg, 1 by r, so g of s into h of s, I will write it as, it is kt into ksg. Okay, kt into ksg. Then g of s is what? Kps upon 1 plus tps. So I will write it as kps divided by r, and what will be here? Whole divided by 1 plus s into tsg of s, 1 plus s into tt. Okay, here will not be s. 1 plus s into tsg, 1 plus s into tt. So I will write it as here like this. And what will be here? It is 1 plus tps into s, plus sign will be there. And if you see, what is your input? Input will be equal to, it is delta pd upon s. Already we have seen this. Delta pd, or you can say this is delta pd of s upon s. Treat this as a equation number 1. I think you all have understood why we have taken like this, and here the minus sign will be as it is. Why? The simple reason is nothing but what? Here if you see, the simple reason is here the input is negative, so that's why here it will be what? 1 plus g of s into h of s, and here the input negative, so this negative sign will be as it is here. So we will get this expression as delta f of s upon delta f of s when delta pc equal to 0, because we are talking about the case A when free governor operation is. And here if you see, okay, let me first tell you about this transfer function. We know this is your g of s. Okay, then if you see, this will be your c of s output, r of s is the input, and here if you see, this is negative, this is positive. Okay, so this will be your, suppose, h of s. So how you can write an expression for this? How the transfer function will be? Here if you see, the transfer function will be like this. It is nothing but what? Why this plus sign is there? This plus sign is there because here input is negative. This input is negative. Okay, so therefore we got here g of s upon 1 plus g of s into h of s. And why this minus sign? Because here if you see, this input here you got as a negative. So therefore I will write it this expression. Now we know what is a final value theorem. Let me first delete this because we have to draw it later on. I will write here final value theorem. Now what is a final value theorem? Final value theorem. How we can write it? We can write it like this. Final value theorem will be equal to x of infinite will be equal to limit s tends to 0 s into capital X of s. So with the help of final value theorem, I can write it as delta small f of s. Now, or you can say not f of s, this is delta f at, I can write here, at steady state condition, because we are talking about steady state condition when delta pc equal to 0. What is the formula? Limit s tends to 0 s into delta f of s, and this condition when delta pc will be equal to 0. So we know what is delta f of s when delta pc equal to 0. This term, you have seen this right hand side term. So this right hand side term will be equal to this. So let me write this expression. How I can write it? Let me write this first, which will be equal to limit s tends to 0. So here this s will be as it is. So this is your s. Okay. And what is delta f of s? Minus. So I will take minus sign outside here. So now how I can write it here? I can write it like this. It will be equal to what? It will be equal to kps upon 1 plus ksg into kt into kps divided by r whole divided by. Now here we have to take some assumption. What is assumption? This, let's say tps, this tsg, this tt. If you solve this, then you will get it as a 1. You will get it as a 1. So tps is 1, suppose tsg is 1, tt is 1. We are assuming these time constants are 1. So here we will get it as 1. Here also 1. That's why this term is 1 here. And what is this here? Into delta pd of s upon s. Now this s and this s will get cancelled. Now what I want to do, just a minute, there is one correction. Let me correct it. Let me again remove this, because there is one correction. What correction? Let me take this. Okay, I will remove this first, because I want to tell you why this particular term is there. So let me correct this. Here there is no assumption. We are not talking about let's say tps equal to tsg equal to 1. Unfortunately, the whatever sentence that I have used earlier, it is wrong. So why this particular term is there? Let me write it again. Then you will be able to understand why we have written like this. So I will write it like this here. Therefore, delta f when delta pc equal to 0, what is this expression? Limit s tends to 0, okay, s into what is this? Minus kps. This was the equation, minus kps 1 plus s into tps, okay, plus ksg into kt into kps divided by r, here divided by 1 plus s into tsg, 1 plus s into tt. I will close this, and this will be delta pd upon s. This was the original equation. If you see this delta f of s, this is nothing but your delta f of s. Now if you see this s will get cancelled, it's okay. This s will get cancelled. But here what is limit s tends to 0? So how I can write the expression? Delta f when delta pc will be equal to 0 will be equal to what? Minus kps whole divided by, here put s equal to 0. So therefore we will get only 1, because this term will be 0. This is the reason why the 1 was there here. Plus ksg into kt into kps divided by r whole divided by, put s equal to 1, because limit s tends to 1, sorry, s tends to 0. So put s equal to 0. So what we will get here? I will get it as 1. Here also I will get it as 1. So this is your expression into delta pd as it is. So take this as a equation number 2. So here input is delta f, or we can say output is delta f, input will be delta pd. Now while the gain kt is a fix for a turbine and kps is also fixed for the power system, ksg, that is the speed governor gain, is easily adjustable by changing the lengths of the various links. Already we have gone through it, ABC linking mechanism and CDE linking mechanism. So let us, for a simplicity, we will take ksg into kt is nearly equal to 1. So what you will get? Will get, if you put this expression in above equation, so delta f at steady state when delta PC equal to 0 will be equal to what? Minus kps upon 1 plus kg into kt is 1, so I will write it as kps upon r. I will put it here bracket into delta pd. So let me write this expression again. Let me write this expression. How I can write? So therefore delta f when delta PC equal to 0 will be equal to, if I divide numerator and denominator by kps, then I will get it like this, minus 1 upon kps plus 1 by r, okay, into delta pd. Now we know what is 1 upon kps. Already in a previous video we have gone through this generator load model. We have seen what is 1 upon kps. It is nothing but your d, because kps was equal to 1 by d. So I can write it as minus 1 upon, this will be what? This will be d plus 1 by r into delta pd. So where already we have gone through this, kps will be equal to what? It will be equal to 1 by d. And what is this d? D is nothing but load demand factor. Load demand factor. How we have written this load demand factor? It is dabba pd on gamma f. Already we have gone through this in the previous video of generator load model. Now the above equation relates change in the required in frequency because of change in the demand, where this R is nothing but what? It is R is nothing but it is regulator. So I write it here delta F when delta PC will be equal to 0. Now the speed regulation R is naturally so adjusted that change in the frequency delta F is a small, we can say of the order of 5% from no load to full load. Therefore the linear incremental relation can be applied to this particular equation. I will take this as a equation number 3. So the linear incremental relation can be applied to equation number 3 from no load to full load. So if you see, I am going to draw this particular diagram. Here what is the relation? If you see, when delta PD increases, there will be change in the frequency, or you can say frequency decreases. Frequency decreases. So therefore if I plot a graph, then I will get a one graph. So directly I will copy here, instead of drawing this I will copy here, I will get this particular graph. Here what we have taken, please compare this equation 3 with a straight line y equal to mx plus c. So on y axis what we have taken? Delta f, but instead of delta f in a percentage we have taken this as a frequency. So this is delta f, we can write it as delta f in a percentage. Then there is no constant term, c term is not there, m and x is there. So what is x? X is nothing but change in the load demand, but it is again in a percentage load, or you can say it is percentage PD. So if you draw the graph in between these two, you will get this particular curve where this particular line has a slope or the droop, which is what? Minus 1 upon d plus 1 by r, which will be equal to minus r. Now why it is minus r, that I will tell you later on. But is what? This is called as a droop. So this particular characteristic is called as droop characteristic. Now the question is, why it is like this? Why this particular diagram looks like this? Because if I draw a diagram, here I will see more the load, okay, let me take this, more the load or lesser the load, here the change in the frequency is smaller. But as soon as, if you see along x-axis, if I am increasing this, let's see, if I draw this point, when 20% loading is there, then frequency will be, let's say it is 102. When 40% loading is there, then your frequency, change in the frequency is going to reduce because load is more. So it is, let's say 101. So therefore if you draw the curve, then what you will get? You will get it like this. For minimum it is like this, because this is your demand. Let's say it is 20% demand. So therefore whatever change in the frequencies, let's say suppose from 50 hertz, suppose if it is changed to 49.5, okay, then whenever it is 40 megawatt or 40 megawatt load, increase in the load is there, so therefore let's see there will be decrease in the frequency again, let's say it is 48.5. so likewise if you draw and if you plot these points, if you plot the curve here, then you will get the curve is like this. So why the nature is like this? The reason is whenever load increases, there will be decrease in the frequency. Now this figure shows the steady state load frequency characteristic of a speed governor system. On the y-axis we have taken percentage change in the frequency, which starts from 100 and it stops at a 5, because we know the tolerance band is of 5%. And here we have taken on x-axis, if you see on x-axis we have taken here loading condition. So the characteristic shown below is nothing but what? This is your droop characteristic. As the load increases, there will be change in the frequency, and whatever droop, the another name for the droop is nothing but a slope, which is -1 upon d plus 1 by r. Now the power system parameter, which is this damping factor d, is generally much smaller compared to that of your regulation. Typically this d has a value of 0.01 per unit megawatt hertz, and this regulation has a value of which is of generally 1 by 3. So therefore as the d is very small, so I can neglect this d. So how I can write it like this? -1 upon this d is neglected, so 1 by r. So what it becomes? It will be minus r. So that's why here we got this as a minus r. So I can write this expression again as delta f will be equal to minus r into delta PD. Consider this as a equation number 4, where this r is nothing but what? It is your speed governor regulation. The droop of the load frequency curve is thus mainly determined by which value? It is determined by value r. So this is the case 1. Now we will solve for the case B. Now in the case 1 what we did? Delta PC was 0 and delta PD was changing. Now here delta PD equal to 0 and delta PC is going to change. So this particular case is called as a controlled case. Why it is called as a controlled case? Because simple. Now here the change in the load demand is 0 and there is a change in the speed changer setting. So how we can draw the diagram again? If you see, now what I am going to do, I am taking this input and I am making this input as a 0. So therefore I will draw this, redraw the first diagram as, let me open this diagram. I will directly copy paste because already I have drawn this diagram. So for a case B, this particular diagram will be there, where delta PD equal to 0 and delta PC alone is acting here. So how we can solve? Again the same thing, delta f of s when delta PD equal to 0. Now here if you see, this total term is nothing but g of s and this is nothing but your h of s. This is nothing but your what? H of s. So how we can draw here? Input is positive, so therefore I will write it as g of s is what? Kg into kt into kps. So I will write it like this. So directly if I write the equation for g of s upon 1 plus g of s into h of s. Okay, so how I will get this? Here if you see, now the feedback is negative. Here the feedback is negative, input is positive, that's why it is plus. Feedback is negative, that's why this will be a plus. Okay, and in the previous also, if you see this case in here, so as input was negative, that's why this is negative. But here feedback is positive, so here you will get it as a plus. So let me draw this, Kg into Kt into Kps upon 1 plus s into Tps of s, 1 plus s into Tsg, don't write this s again, and 1 plus Tt into s. Okay, plus what will be the next term? It will be Ksg into Kt into KPS divided by R. So from this expression, G of S upon 1 plus G of S into H of S into what is this? Delta PC of S upon S. So this is output, this will be your input. So let's take this as a equation number 5. So again what we will do, we are using a final value theorem. So how you can get using final value theorem? Delta F, small f, when delta PD equal to 0. So again I am going to apply it directly, S into delta F of S when delta PD equal to 0. This is the condition, and here limit S tends to 0. So directly I am going to apply this, and I will get the expression as delta F when delta PD equal to 0, which will be equal to what? Which will be equal to here, when limit S tends to 0, then you will get this thing. You will get this thing. I write it here, S as it is. Okay. Then here, when we put directly limit S tends to 0, then we will get it like this: KSG into KT into KPS whole divided by 1 into 1 into 1 because S tends to 0 plus KSG into KT into KPS whole divided by R and delta PC upon S. So this S will get cancelled. So we will get this expression. Now again we will make this KSG into KT is nearly equal to 1. Before that, let me take this as a equation number 6. So how I can write this expression now? So therefore this delta F when delta PD equal to 0 will be equal to what? KSG into KT is 1, so we will get it as KPS upon 1 plus KPS by R into delta PC. So if I write here expression, then I will get the simple expression as delta F when delta PD equal to 0. So if I divide numerator and denominator by KPS, I will get 1 upon KPS plus 1 by R into delta PC. So we know what is 1 upon KPS will be equal to D. So I got this as D plus 1 by R into delta PC. So here this is delta F when delta PD will be equal to 0. This is expression number 7. So if you observe carefully this expression 7 and this particular your expression, we can say expression 3, both are same. Just the difference is here in 3 it is minus and here we have written delta PD, and here in last expression it is plus and it will be delta PC. Now from equation 3 and the equation 7, if the speed changer setting is changed, which is caused by a delta PC, while load demand is changed by a delta PD, then the steady state change in the frequency is denoted as. Now we know that I can write this expression as from equation 3. So I write it as from 3 and 7. We will use a superposition in the mathematics. So what we will get? Delta F, left hand side will be as it is. Just the thing is what? D plus 1 by R. In the first case it was minus sign. In the second case it is plus. So it is delta PC minus delta PD. If you multiply this, then you will get this delta PC into this term, you will get equation 7, and minus delta PT into this term, you will get equation number 3. So I will mark this as a equation number 8. So from the above equation, if you make if this delta PC equal to delta PD, that is whatever will be the demand, that much amount of commanded power is there, then change in the frequency will be equal to 0. So frequency change caused by the load demand can be compensated by changing the setting of a speed changer. So as far as there is a change in the delta PD, if there is a corresponding change in the delta PC, then your change in the frequency, that is delta F, will be equal to 0. So this is what is the steady state analysis of single area load frequency control. So here we have seen two cases, case A which is pre-governor operation and case B when delta PD equal to 0. If you have any doubt, please feel free to ask. Thank you for watching this video. Once again, thank you.